Thank you. Let me know whenever that happens. It usually just means I forgot to click a button. Great. Then I missed the first part. Sorry if you're online. You just missed this slide. That's all I had. And I went over the survey results. Whatever. So apologies for that. Okay. Yeah, please stop me if that ever happens in the future. I appreciate that because this is also useful after the fact, even if you're here in person. Okay, next slide. Do not need to know it. If you blank out and completely tune it out, I'm never going to ask you a question like this in the test, but it is one of the few cases in this class where I teach you something. What I'm about to show you is relevant for literally every single person, assuming you pay the bills. Pay bills. It's kilowatt hours. It's what you all get charged for on your electric bill. If you're paying for electricity, you are getting charged based on the kilowatt hours you consume. Kilowatt hours is something most people have no idea what it means, but I just told you, watts is power. It's kilowatts, so it's 1,000 watts. And hours, if we just do P equals W over T, so if we look at that equation, if I multiply power times time, it gives you the energy you use. That's what a kilowatt hour is. It's literally the unit for power times the unit for time. That's how much energy you're using. A kilowatt is how much per second. An hour is some amount of seconds. Ta-da, that's what you get charged for. The more kilowatt hours you use, literally the more energy you use, the more joules. It's not quite a joule because the units are kind of funky because it's kilo and it's not seconds, but it does the idea. So, if you want to find the cost of any electrical appliance in your house, and every single electrical appliance is using it's using electricity, it has a wattage associated with it. Some of them are labeled on it like a light bulb. Some of them are a little trickier to find. You'll have to learn an equation in physics 2 to actually, for your fridge. For some reason, your fridge doesn't list it. I had to find the wattage for my refrigerator when I bought a generator during the hurricane because I needed to figure out whether the generator could supply the amount of energy that my refrigerator needed. Turns out you'll learn in physics 2 there's an equation called PIV, P equals IV, current, voltage, multiply that gives you the power, whatever. Future things to worry about. Take your wattage. Let's just pretend we have a 100-watt light bulb, which hopefully you don't need more. Those are incandescent. If you have an LED light bulb, it'll be about 10 watts or 14 watts. It's literally 10 times less the energy, maybe 8 times less, depending on your perspective or the math. All right, great. You take that, you convert it to kilowatts. So a 10-watt light bulb is 0.01 kilowatts. Just hop the decimal place 3 places over. Great. Then you're going to take that and you're going to multiply it by the hours used. So let's just pretend that you have this light bulb on for 3 hours a day. Great. Then you multiply this by the cost per kilowatt hour. This is about 14 cents. How do I know that? Because in my last class, I pulled open there you go. Here's my electric bill. So if you have an electric bill, probably something, I don't really look at this monthly. It's one of those things you just got to pay it. So I just kind of have it set to auto pay. That might be the case for you as well. But if you look at this, they tell you, so there's various charges. The energy charge is paying for the company and their infrastructure and all that kind of stuff. The fuel charge is literally the cost for the coal and the natural gas that's used to actually make the electricity. Most of our electricity is made from burning things. That's the fuel that you're paying for here. And then asset, I've heard that's the power lines and things like that. Anyway, every 1 kilowatt hour, if you kind of add this up, so it's 9.9 cents per kilowatt. This one's 3.6 cents per kilowatt. This is 0.227. I used 916 kilowatt hours last month or this month. I don't quite know there's a time frame. Last month. If you just add up all these numbers, it basically comes out to 14 cents per kilowatt hour. Each of these just gets multiplied. They just break it up to show you where the money's going. But 14 cents per kilowatt hour is about what it is. For Duke, for me, around here. Yours should be the same. It's the same everyone gets charged the same. Per kilowatt hour. So great, it's about 14 cents. So long story short, if you want the total cost of any electrical device in your house, get its kilowatts. So in case of this light bulb, 0.1. Multiply it by the hours, 3 hours. Multiply it by the cost per kilowatt hour. And that comes out to, I think, 4.2 cents. If you plug that in, 0.042 cents. So that's how much it costs to run that 10-watt light bulb for that day. Again, you don't need to know this. I'm not going to test you on this. But it's something that you are experiencing every month. You got to pay the electric bill. Now, to that end, you are not really worried about yes, light bulbs can actually save you some money. If this was instead an incandescent light bulb, it would be 10 times that cost. Because the wattage would be 10 times as much. So that would be 10 times as much. So it costs 10 times as much. If you do that per day, that's 38 cents extra per light bulb. You multiply that by 365. Long story short, if you just spend the money to change all your light bulbs from incandescent to LED, you'll recoup that cost in a year. And then each year save money. It doesn't take long to re-earn. So, highly recommend it. It's one of those easy ways. Save a few bucks a year. You probably won't notice it, but it does change the numbers in your bank account. So, the two major things that are going to be your major costs are the things that both have the highest wattage and run for the most hours. The ones that use the most energy per second and run for the most seconds. Refrigerator and AC unit. Those are the major ones. Really, your AC unit more than anything else. A few degrees makes a big difference. You probably have arguments with your roommates about all that. Fun things. Okay, so this one, you can kind of go through on your own if you want, but, here, I'll just do it. It's 1.5 kilowatts times 3 hours. I'm not going to spend much longer on this because I've already spent enough. It comes out to 45 cents. So if you run a microwave that's 1,500 watts, which is pretty strong. My microwave at home is pretty dinky, and it's 700 watts. Bigger ones might be like 1,200 watts. And again, what's cool is when you see this, it's literally how many joules per second it's using. That's what it represents. I don't know. I think stuff like that's cool when no one knows what a wattage is on a microwave. Most people you talk to, if you ask them, they would just say the bigger the number, the more powerful the microwave. Sure, that is true, but what the hell is it? It's literally energy per second. That's it. There you go. You can tell your roommate and they'll say, I'm not in physics, I don't care. That's how most people feel about these things, but I think it's cool. All right, don't forget the force of friction is μFn. If the acceleration in the y direction is 0, then Fn equals Fg. There was a question on the test, but that was not the case. A lot of people put Fn equal to Fg. It wasn't the case. We'll talk about those problems on Tuesday. But if A equals 0, then this is true. That's just going to come up in some problems at some point. So that's why I'm mentioning it. The stuff we've learned before is going to come up again. Everything builds. The time you spend on test 1 goes back into everything else. You also need to remember that friction is always opposite the direction of motion. Again, I'm going to kind of zip through these next couple questions. I'm not going to ask one like these on the test, but they're just interesting, and we're going to use the information from them to understand other things. So this one says, I push a heavy box across the floor in a straight line at a constant velocity. Someone else takes a crazy windy path, as shown here in the picture. If friction exists, who had to do more work? Sure. Actually, I said I wasn't going to do it. I'm totally going to do it. I'm going to give you all of 40 seconds. That way I don't feel like I'm using that much time. Go with your gut. Do you think, so me is the red path. Did I do more work on this red path? The blue path is someone else. Did they do more work? Or is the work the same regardless of the path you take? All right, 5 more seconds. 4, 3, 2, 1. So, the interesting thing about friction is the direction of friction depends upon the direction you're going. If you're moving to the right, friction's to the left. If you're moving to the left, friction's to the right. It's always opposite the direction you're going. So why is that relevant? Work is the absolute value of F times the direction you're going times cosine of theta. The end result of that is the path matters. The path matters because it's always fighting. You all know this. You push a box over a far distance, it's harder, right? If you take a meandering route, you're fighting it the entire time. Friction is never helping you. Friction on the box is always fighting you. Friction is technically helping you because it's letting you walk. But ignoring that, on the box, it's always fighting you. So yeah, someone else. They had to do more work. They had to put more energy in because it's always fighting them. It's never making their life any easier here. Fantastic. All right. This next one, I'm going to kind of just give you the answer because it's a little trickier. This one's about gravity. So it's the same idea. Car goes flying off a cliff. There it goes. Another car takes a winding path down the hill and, ends up at the same location. In which case was the work done by gravity greater? And this is one of those where it'd be tricky probably to figure this out just as is, which is why I'm going to straight up tell you it's the same. And the reason this is a different answer, than the last one, is gravity is always down. Friction's always fighting you. But in this problem, sometimes gravity was helping, sometimes gravity was hurting. And so all those effects cancel out, such that the end result is that gravity doesn't care about the path you take. It only cares about where you start and where you end. Because the direction of gravity is set, whereas the direction of friction is not. It varies. So, why did I mention all this? What's the reason I went through this? This is foreshadowing that we're going to find that gravity has an equation. We're actually not going to find the work due to gravity in most problems. We're just going to use the equation for potential energy due to gravity. Like we'll see this in a future slide, but there's an equation for this. And if you want to find the change in potential energy, you just do mg delta y. It doesn't matter what path you take. It doesn't matter whether it's meandering, whether it's a straight line down, whether you zigzag. I don't care. All I care about is where you start and where you end. And that's the work done by gravity. Whereas friction, you have to do F delta X cosine theta. There is no shortcut there's no simple equation for the work done by friction. It is the work equation. So that's the difference here. All right. And the reason this gets into, these are, the fancy phrases for these are conservative forces versus non-conservative forces. Conservative means you can kind of get back that energy. That's conserved. It's able to be recovered. If I lift something up and I drop it, it'll go fast. You can't get back the energy from friction. If I push a box along the floor, I'm never getting that energy back. It's gone. Whereas if I lift an object, I can easily get that energy back by just letting go of it. And then it falls. And it goes fast. And you recover it. So, conservative forces don't care about the path. Gravity, springs, the ones that we're going to give you equations for. Non-conservative forces care about the path, and those are the ones we're going to have to use the work equation for or solve for. So that's just this is going to be happening in the background. If you don't understand this, that's fine. You'll still be able to solve the problems. But this is why I'm going to be able to give you some equations for energy. Whereas friction and applied force, I can't just say, hey, here's the equation. The equation is work equals Fx cosine theta. So, more of a conceptual thing. And yeah, that's all kind of here. So that's just the background it's that conceptual background. All right, this slide, most important slide. So this slide, and I'm going to go ahead and write this out now because we're going to start to see it in a second. This is how we're going to solve basically I've already mentioned this at the beginning, every single problem. I have taught you how to find the work. That's what we just spent the time doing. I've taught you the equation for work. If you want to find the work due to some force, it's F times delta X times cosine of theta. Or there's also power equals work over time. Those are two equations that can get you work, depending on what you might have. Now, I'm going to teach you the equations for the energies we're going to talk about in this class. And there's only 3 we're going to teach you in this class. 3 types of energies we're going to calculate. There's way more than these 3. Way more than them. But we're just going to cover 3 in this class. We're going to cover kinetic energy. We're going to cover potential energy due to gravity. And you're going to see me, another symbol for this is going to be U. And we're going to cover the potential energy due to a spring. Again, another letter for this will be a U. U and potential energy are synonymous. I don't know why we use the letter U, but both of these are correct. They mean the same thing. U, PE, same exact thing. So we're going to add up all our energies that we start with. We're going to go and make a checklist. Am I moving in the beginning? Am I above the zero? Is there a spring? We're then going to say, is anything adding energy to it? Is there any work being done? And then it's going to equal the kinetic energy I end with, plus the potential energy due to gravity I end with, plus the potential energy due to a spring I end with. What I start with plus what I add equals what I end with. This is how we're going to solve every single energy problem. If this looks complicated, I promise you after we do a few of these, it's really, energy is one of the easiest problems, one of the easiest kind of problems to solve. It's the reason why it's so great, my physicists love it so much, is it lets us do problems that actually would be much more unpleasant. And I'll show you some cases of those. A lot of energy problems you could solve with kinematics. There is some energy problems that technically could solve with kinematics, but it would be awful. Like you would need a computer to do it. It wouldn't be something you all could actually do, even though the principles apply. Energy makes problems much easier. And there's no vectors. There's no x and y components. I'm not going to say what's the x component of the kinetic energy. It doesn't exist. It just has kinetic energy. You don't worry about components. Everything's magnitude. All right, so now I need to teach you how to find these three types of energies. I've taught you how to find work. Now we're going to find these three types of energy. And then we'll put it all together, and on Tuesday, that's when we'll solve a bunch of problems, just practicing this. So, one equation at a time. Kinetic energy was actually the first one that was actually discovered. That's what started the whole energy thing, so that's why we're starting there. All right, and this is probably something you've learned before. If you haven't, that's all right. I'll teach you, but this is just to show you. You've probably seen this before. You've probably seen kinetic energy before. How does an object gain kinetic energy? Is it by going faster, going higher, charging it up, or absorbing heat? All right, we'll go like 10 more seconds. This is one of those, you know it or you don't. And it's all right if you don't, because I'm about to teach it to you. All right, in 5, 4, 3, 2, 1. All right, how do you gain kinetic energy? You go faster. Great, that's the easy way. If you're not moving, you got no kinetic energy. The word kinetic means motion. Boom. Yeah, we did it. Great. Kinetic energy. First one discovered. Some guy, forget his name, discovered that if you calculate mv squared, stuff happens. You calculate mv squared at the end, they're proportional to each other. It was like conserved. So bam. First one discovered, proportional mv squared, words I just said. Yay. And then here's derivations that are hidden because they have things that we're not going to be happy about. Integrals. So if you like calculus, you can look at these. You can derive it from work. Ooh, so exciting. All right, great. There's the equation. It's 1 half mv squared. You've probably seen it before. M is mass, v is velocity. And remember, there's no x and y components of this. It's just, hey, put the magnitude of velocity in, and that's its kinetic energy. 1 half mv squared. The unit is joules, because that's the unit for all the energy. And we've kind of been referencing this the entire time. Remember I kept telling you if you do work, you increase the energy. You make things go faster if you push them. You make the kinetic energy go up. If you push it opposite the way it's going, you make it slow down. You make this go down. So we've been referencing it kind of the entire time. Nothing crazy, pretty straightforward. Most of these all the energies, the equations are super straightforward. All right, so now I got a couple questions about them. And the reason I ask these kind of like freebie, simple questions is because if you understand the ideas behind these, you'll do a better job solving the problems. if I just go through and just solve a bunch of math problems with these, it doesn't actually give you any conceptual understanding. And it may seem like I don't need, on the test, I'm not doing the concepts. You secretly are. Without the concepts, you're far more likely to get stuff wrong. It's more than the math. So, this question is going to come up with every single energy. Can kinetic energy be negative? This is one of those checks. If you ever find, can it be negative? If it's impossible to be negative and you ever calculate a negative kinetic energy, something's wrong. If it can be negative and you calculate a negative, great, that's fine. But these kind of checks are super useful. Oh, and I'll even put the equation for you all. Kinetic energy is 1/2 mv squared. All right, we'll go like 10 more seconds. Five, 4, 3, 2, 1. All right. Can it be negative? We just checked through it. Can mass ever be negative? No. As far as we're aware, there's no such thing as negative mass. If there was such thing as negative mass, it would, if there was a negative mass, that would mean if you put it in a gravitational field, it'd go away from the thing. So if you had a negative mass and I put it near Earth, it would fly away from it. We have yet to discover anything that flies away from stuff due to gravity. So, as far as we're aware, that can't be negative. Can velocity be negative? Sure, but it's squared. So it's going to turn to positive no matter what. Your kinetic energy can never be negative. The lowest value it can be is 0. Otherwise, it's bigger than that. Now, something I also want to point out here. Ideally, I'd ask a question about this, but just for the sake of time, I'm just going to chat about it. I want to continue to remind you all that so many of the variables I teach you all are all relative. Like if I asked you right now, what's your velocity? What's the answer you want to say? 0, right? Relative to what? The Earth. Relative to the Earth, my velocity is 0. Relative to this room, my velocity is 0. Relative to the sun, your velocity is incredibly high. So your kinetic energy right now, if I said, what's your kinetic energy right now? The answer, there's an infinite number of correct answers. Generally, we refer to the Earth as our reference frame. But I mentioned that it doesn't matter how much your energy is. It matters how much your energy changes. Every single problem we talk about, when we talk about energies, it's all about how your energy changes. So like if I said my energy, I said it relative to the sun, you're traveling really fast. You have a lot of energy. If the Earth suddenly came to a stop, your energy would have changed drastically because you went from going really fast to nothing. Same thing actually if you all, well, it's kind of weird looking at the room and saying all that. But so anyhow, just something to keep in mind. Relative. There's a whole field of physics called general relativity, and it gets into all that weird stuff that can happen. Anywho, it's really, really important. All right, this next question I like a lot because there is a couple ways you can do this, and I will do both ways. What has more kinetic energy? A 1,000 kilogram car going 30 meters per second or a 2,000 kilogram truck going 15 meters per second? I purposely picked numbers such that the second object has twice the mass, but the second object has half the velocity. That is purposeful. And then you have to decide what that means for this. Here's the equation. Your logic should always match the equation because an equation is just an expression of logic. Is it a 1,000 kilogram truck with more energy, 2,000 kilogram truck with the same? All right, we'll go like 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so the most straightforward way of doing it, like the most blunt, obvious way of doing this is literally just calculate it. Like, you know, I gave you all the numbers you need. You can just straight up calculate this if you want. So 1,000, for the car, it's 1/2 times 30 squared. For the truck, it's 1/2 times 2,000 times 15 squared. And if you do so, you know, this one's going to be some silly large number because vehicles have a lot of energy with them, which is why they're so scary. Why it's scary, because if it hits something, that energy changes from a lot to nothing very quickly. And that gets transferred to whatever it hits very often. And then, yeah, if you do this one, you know, the truck is smaller, 2.25 times 10 to the 5. So, yeah, the car has more. Great. That's one way to prove it. Just literally plug in the numbers. Like that totally works. The other way, and we're actually see this in the next slide, is, so remember I've done this before where I have an object and I write it in terms of the others. So the mass of the car is 1/2 the mass of the truck. I'll put these as MCs and M truck. It's half the mass. The velocity of the car is twice the velocity of the truck. Just write in the expressions there. Why is this useful? All right, I'm going to do kinetic energy of the truck is going to be 1/2 mass truck, velocity truck squared. Great. Kinetic energy of the car is 1/2 mass car, velocity car squared. Great. Nothing exciting yet. Then what we can do, though, is we can swap these in. So I can take this mass of the car and I can swap in this relationship. So I can say it's 1/2 times 1/2 mass of truck. Then I can do the same thing with the velocity, is I can swap that in. And we're going to do that literally in the next problem. 2 times velocity of truck squared. Now what we're going to do is I'm going to pull out all these numbers to the front. So I'm going to keep this 1/2. So I'm going to keep this 1/2 that was in the front there. I'm going to pull out the 1/2 that was in front of the mass. I'm going to pull out the 4 because 2 squared is 4. And we're going to pull that out. I still need to keep this 1/2 here. I don't want to pull that as well because at the end of the day, what I need to do is say that this is the kinetic energy of the truck. So long story short, the kinetic energy of the car is equal to 2 times the kinetic energy of the truck. So this is something you can do where you can do stuff with the equations, and it seems like it took a bunch of work, but this is much easier. Like I didn't need a calculator for this, which is nice. And what's the takeaway from this whole problem? The takeaway from this problem is velocity matters more. It's squared. Whatever happens to velocity squares. If you're going 10 times as fast, then you're going to have 100 times the energy. If you're going 4 times as fast, you're going to have 16 times the energy because it's squared. And so, like, obviously the equation is squared, but oftentimes people forget to, whatever happens to velocity also has to be squared. And we see that here. If you look at the numbers up here, it all works out. The velocity of the energy of the car is twice that of the truck. So the numbers match the logic. Yay. Velocity is where you're going to get most of your energy from. Mass does matter. It's in there. If you have 10 times the mass, you'll have 10 times the energy if you're moving the same velocity. But all right, so let's see if all that made sense. So instead of me giving you a bunch of numbers and having you do this, now I'm just going to ask you, what happens to the kinetic energy if I half an object's velocity? And there'll be a problem like this, I think, on the upcoming quiz where it says the mass changes by this, the velocity changes by this. What's my energy? I think there's one like that. So will my kinetic energy be twice the original? Will my kinetic energy be 4 times the original? Will it be 1/2 the original? Or will it be 1/4 the original? If I half my velocity, and that's all I change. All right, we'll go like 10 more seconds on this. With these problems, if you're unsure what to do, you can always make up numbers. You can make up the mass as 1 in the beginning. You can make up the velocity as 1 in the beginning, and then just change whatever it asks you to change and see what happens. Totally a viable option. All right, in 5, 4, 3, 2, 1. All right, so we just write the equation. Kinetic energy equals 1/2 mv squared. We say my new energy is going to be 1/2 m, but my velocity is now half. Put a half in front of it. You square it. 1/2 squared is 1/4. So I'll write that out. 1/4 velocity squared. Yank that thing to the front, and boom, it's 1/4 the energy because the half got squared. Great. Again, I mentioned this just a few seconds ago. You can make up numbers. If you want, make like your original mass. Find the kinetic energy due to something with a mass of 1 and a velocity of 1, and you'll get 1/2 joules. How exciting. All right, let's half it. If I half my velocity, instead of being 1, it'll be 1/2, and you'll get 1/8. And you compare those two. And so that if that makes you feel more comfortable, make up numbers and then just change them like it tells you to. Double them, triple them, half them, whatever it tells you to do that. Totally works. You're doing the exact same thing at the end of the day. I like this method down here because I don't have to then compare the two. I just pull out the numbers, but all right. How do we do on that? Fantastic. Yeah, it really does just come down to don't forget that it's squared. It matters. Whatever happens to it needs to get squared as well. All right. And we're back to this thing again. Why? Because we're going to use it to solve the problem. Like, again, this is the most important thing. Everything I'm teaching you is just the pieces of this. We did work. I have now taught you one type of energy to consider. So now we're going to do a problem that has the one type of energy and work. And we just kind of build from there. Reminder to you all, these are scalars. You don't have to worry about left, right, up, down, any of that stuff, which is nice. Okay, calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers per hour and a distance of 120 meters, a fairly typical distance for a non-panic stop. Yeah, you'd be surprised if you hit the brakes how far your car actually goes. It's way more than you'd expect it to be, which can be, that's why speed limits exist and all that. Kid runs in front of you, brakes are only going to do so much. How long it's going to take you depends upon how fast you're going, more so than anything else. All right, great, so we're going to do that. Then we're going to do over 120 meters. Then we'll do it instead over 2 meters. And that's the problem. I'll be blatantly honest with you. This problem you can totally just do with kinematics. So I'm just going to show you how to do it with energy instead, because you know how to do kinematic stuff. They're both good. Is one better than the other? No, in fact, you're doing the exact same math either way. But yeah, if you look at this and say, can't I use kinematics? Yes. But this is just a good example to show you how to solve this with energy if you chose to do so. So we write down our givens. We got our mass is 950 kilograms. Oh, and before I even begin, once you decide something's an energy problem, it's going to be energy initial plus work equals energy final. Like that's, I've said it a bunch of times, that's going to, almost like F equals MA for force problems, energy problems, this is the one you use. So I'm just going to chuck that there for now. My initial velocity is 90 kilometers per hour, which we're going to need to convert. And that's going to be 90 E3 over 3,600. 60 minutes times 60 seconds, converted kilometers to meters. It does come out to a nice number, which is convenient. 25 meters per second. My delta X is going to be 120 meters. That's my displacement, distance, however you want to phrase that. Final velocity is 0. And that's kind of all the numbers. There's the 2 meters, but that's part B. We are solving for force. All right, so we have our equation. I've only taught you one type of energy, kinetic energy. So then we just ask our, basically, in this case, because I've only taught you one type of energy, we have our energy initial plus our work equals our energy final. There is other types that'll show up, but for now, that's all I've taught you. That's the only type. So we just got to put those in there, and then we ask ourselves if it even exists. Am I moving in the beginning? Yeah, I have kinetic energy to begin with. Am I moving at the end? No. So this term will turn to 0. If the final velocity is 0, it's going to equal that. But for now, if you really want, we'll leave it there. And then the work equation. So we're going to be like, why is this useful? Work is force times delta x times cosine theta. So if we can find the work, then we can find the force, and all is well in the world. So yeah, this is a really simple conservation of energy problem. Only one type of energy. So we just put in the numbers. 1/2 times 950 times 25 squared plus, I'm just going to solve for work for now, and then I'll plug it into the other one. If it was me doing, I am doing it, but if I was doing this on my own, I'd actually put the work equation in there. I'd be preferential to that, but I'm going to do it in 2 pieces because sometimes people prefer that. 0 squared, that disappears. So long story short, work's going to equal negative, and I'll equal 0, just to make sure people don't get too. And I'm going to write out every step, actually. Better safe than sorry. It takes me more time, but it'll result in less questions. 2.97 times 10 to the 5 plus work equals 0. So therefore, work equals negative 2.97 times 10 to the 5 joules. We always stop and say negative. That's weird. Does that make sense? I'm losing energy. I'm getting slower. Work is negative. If I was getting faster, work would be positive. I'm getting slower. Work is negative. I'm losing energy. Makes sense. I went to moving to not moving. That's the thought process when you're solving these problems when it comes to positives and negatives with work. Don't forget to do that. That's why we spent the time on that. Calculators can spit out numbers all day. That's not what we're getting trained to do. Calculators can do all this. A lot of what you all are getting trained to do is say, does that make sense? Reasoning, thinking, that's the more critical skills. All right, so then we're going to use this blue equation with our work. So negative 2.97 times 10 to the 5 is going to equal my force times my distance times cosine of the angle. My car is moving to the right. The brakes are going to make it have a force to the left. This is going to be cosine of 180. Not a huge deal. If you miss this, it's not a huge deal. But the benefit here, if you don't do this, it just doesn't make sense. I have a negative answer equaling a couple positive absolute values. Where does the negative come from? This equals -1. It gets rid of the negative for us. Otherwise, a negative can't equal an absolute value. Anyway. So my force equals my magnitude of the force. So this negative will cancel with this negative. 2.97 e to the 5 over 120. And that equals something. 2,475 newtons. The previous answer, I think they rounded for some reason. There was some rounding that happened at some place. Oh, yeah, my number here wasn't exactly that. Whatever, close enough, 1 to 2%. Great, and then part B is literally the exact same process, just divide by 2 instead of 120. So I'll leave that one for you all because it's good practice. Part B is, if you're not sure what's different about Part B, then that's a good thing to kind of work through and figure out. So there you go. Kinetic energy. Yay. Nice and straightforward. Building towards the end. 1 energy down, 2 to go. But yeah, again, you all could have done this with kinematics. You could have found the acceleration. You could have multiplied that by the mass, and you could have gotten the force. If you actually recognize the math here, if you had done kinematics, you would have used Vf squared equals V naught squared plus 2a delta x. That's how you would have found acceleration. Oh, look, a velocity squared. You did the same math without realizing it. You squared velocities. There was a mass involved. There's a 1/2 term. If you move that over, it's multiplying by 2. Like you can, if you play around with it, you can see it turns into Vf squared equals V naught squared plus 2a. Up to you. All right. What is the work done by gravity? This is the last time we're going to kind of reference, or this little section, we're going to use the work done by gravity to get the equation for the energy due to gravity, and then moving forward, we won't deal with the work due to gravity anymore. We'll just use the equation for energy instead. So, we're going to use this to derive the equation. That's the whole purpose of this question. This is one piece of deriving the equation for potential energy due to gravity. Well, one piece, it's actually the entire piece. What is the work done by gravity if I lift something straight up from some initial height y naught to some final height yf? It matters that I'm lifting it straight up. If you ignore that and do not incorporate that into your question in some way, then you will get it wrong. Is it mgf minus mg naught? Is it mg parentheses yf minus y naught? Is it negative mg yf minus y naught? Or is it yf minus y naught? All right, go like 10 more seconds. In 5, 4, 3, 2, 1. All right, so I told you all like getting lifted straight up matters. If we're going straight up, that means the direction we're going is up. Gravity is down. For now, we're going to put that there. Work is the absolute value of force times the displacement times cosine of the angle. In this case, we want the work due to gravity, so it's going to be the absolute value of mg times delta x times cosine. If they're opposite directions, it's 180. If you're lifting something up, if I toss something upwards, gravity's going to slow it down. Gravity's going to take away energy. So, absolute value, mg, and I put x here. I'll go ahead and put delta y. Y final minus y initial. That's just the definition of change. And there's a negative sign in front because of the negative 1. Now, something to point out. So you all, this is actually where the equation for potential energy comes from. So we're going to see on literally the slide 2 from now that we're going to find that the potential energy can be, again, it could be a U, it could be a G, it means the same thing. We're going to find that it's mgy. And so, debating whether to show this now or later. I'll show it in a future slide. It's mgy, and we're going to find that the change in potential energy is the negative work done You can kind of see it here if you look here. There's a negative. So there you go. This is just deriving potential energy. It's mgy. Like that's what we're going to use moving forward. The negative, again, comes down to the direction. If you're going upwards, gravity is causing it to lose energy. It's all about whether you're gaining or losing. All right, next question for y'all. How high up are you right now? Are you 0 meters high, 3 meters high, 6.371 times 10 to the 6 meter high, negative 10 meters high? Don't overthink it. 30 seconds, just pick something. Pick whatever feels most comfortable to you. All right, 10 more seconds. If you haven't picked something, just go with the one you like the most. All right, 5, 4, 3, 2, 1. So this question was basically the same as one of the first questions I asked you at the beginning of the semester, which is, where is Demoduck located? And the answer is, it depends what you're measuring with respect to. What am I measuring with respect to? I didn't specify, so every single answer here is right. If you measured from your feet, you got to have some spot to some spot. If you're going to measure where something's located, what are you measuring? What object are you measuring? And where to? If it's your feet to what their feet are touching, that's 0 meters. If it's your feet to... We're technically not on the first floor, so if it's, for some of you, it's like 3 to 5 meters. If it's from your feet to literally like the dirt outside, that'd be like 3 to 5 meters. The third answer is from your feet to the center of the earth. And the part D is from your feet to the floor above us. You are negative 10 meters below that. Where do you measure with respect to? If you're below it, it's negative. If you're above it, it's positive. So, every single answer here is right. And to that end, your potential energy could be any value. 0, not 0, big number, small number, whatever. And the reason I'm mentioning this, we don't actually care about what your energy is. We care about your change in energy. That's why the equation that we're using in this entire thing has an initial, has a final. You're always subtracting the two. You're always doing final minus initial at the end of the day. We only care about the change in energy. Just like with kinetic, you could have a bajillion kinetic energy. So yeah, they're all right. Yay. Doesn't matter which one you pick. And this is just getting to the idea that it's all relative, but the change is not relative. Just like position. I don't care what you say your position is. If you move 2 meters to the left, it's going to be a displacement of 2 meters, regardless of what you're measuring with respect to. All right, so mgy, that's the equation for potential energy. You might have seen this previously as mgh. I like y better because y is position, whereas h actually I think mixes people up. People think height and they try to find height. Y is just where you're located. So multiply your mass times g. This is positive 9.8. Do not put a negative in here. Why do we not put a negative in here? Remember you all, this came from the work equation. And the work equation was absolute value of the force. Absolute value of negative 9.8 is positive 9.8. So, do not put a negative here for G. It is positive 9.8. And you get to decide where 0 is in a problem. I generally advise you, pick either where you start as 0 or where you end as 0. That way you have less math to do. That way one of the terms goes away. But it's a choice you get to pick. It's very rarely told you in a problem, make this 0. Very rarely do I tell you that. You get to decide. And you'll get the same answer either way. Great. All right, now we're going to practice this one. Do one more question. All right, what is the gravitational potential energy? And I'm going to actually change this problem. What is the gravitation? I'm going to change all the answers to, this one's 490 joules, negative 490 joules, 50 joules, negative 50 joules. What is the gravitational potential energy for a 10 kilogram object that is 5 meters below the ground? I am telling you in this problem, set the ground as your zero. So this one, I'm telling you what your zero is. Generally, I won't do that, but in problems, if I say find the potential energy, I have to. But all the conservation energy problems, I won't do it for you. You get to decide. And then after this, I got a couple problems. I'll do one worked out problem, then like one more clicker or top hat. And that's my goal for today. That'll get us to a good spot. That'll let us spend most of the time Tuesday just doing practice problems. We'll go like 10 more seconds. Five, 4, 3, 2, 1. So just to draw a picture of this, there's the ground. That's where my y equals 0. I am located down here where my y equals negative 5. So if I'm going to calculate potential energy, it's going to be mgy, which is going to be 10 times positive 9.8 times negative 5. And that comes out to negative 490 joules. Potential energy is the only one of the energy equation I'm going to give you that can actually be negative. It doesn't mean anything special. It just means that negative is a smaller number than a positive number. That's all this means. 10 joules is bigger than 0 joules is bigger than negative 10 joules. These are scalars. It's not direction. This doesn't mean you have a potential energy downwards. This just means it's a smaller number than 0. And that's the purpose of this problem, is just to show you, hey, it can be negative, and that's okay. It doesn't mean anything crazy. All right, so this next slide I'm going to show you, and then I'll kind of show you where it comes from and the purpose of it, and then we'll move on. So you all actually kind of already showed this, that work equals the negative change in potential. And if you're wondering when that happened, you all came up with the following equation. So this was one of the this is one of the previous questions. I said, hey, what's the change in potential energy if I lift something upwards? If you all just rewrite this, mgy final minus mgy initial, and then that one's going to be a plus. So it becomes mgy initial minus, well, here actually, let's leave it as is, like this. Mgy final minus mgy initial is the exact same thing as final potential energy due to gravity minus initial potential energy, and that's, so work equals the negative of that. The only reason I have this slide here is this lets us derive conservation of energy. So work equals negative change in potential. Work equals positive change in kinetic. If A equals B and B equals C, so Where am I going to shove this to make this all work? So work equals negative. Actually, I already wrote that here, so I don't need to rewrite that. Equals kinetic energy final minus kinetic energy initial. Work equals work. W equals W. Great. Let's put this W here, or this W here. Work equals positive change in kinetic. Let's put this W here. This is just to show you that conservation of energy, it's another way of proving it. So change in kinetic energy. So kinetic energy final minus kinetic energy initial equals negative potential energy final plus potential energy initial. And if you just move the finals to the same side and the initials to the same side, potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Yay! What I start with is what I end with. If I add up all the energies I start with, it equals all the energies I end with. That's all this is showing you all. Just connecting everything together, showing it all makes sense. If this doesn't make sense, pretend like I didn't say anything. At the end of the day, I just need you to know, add up all the energies you start with plus work equals the energies you end with. All right. So, this slide, same one. I'm going to mention it because we're going to do a problem. I don't even need, so I guess I should read the problem before I tell you the equation. How long will it take an 850 kilogram car with a useful power output of 40 horsepower? 1 horsepower is 746 watts. Horsepower is literally how much energy per second that vehicle or engine can output. More horsepower means it can put more energy out, which can let it go faster, quicker. To reach a speed of 15 meters per second, neglecting friction, how long will it take if the car also climbs a 3-meter hill high in the process? Shock and awe, the second you realize it's energy plus work equals energy final. Again, that's every single energy problem. We're going to do that. So we write down our givens. We have the mass of 850 kilograms. We have the power of 40 horsepower. So that's going to be 40, and then we're going to multiply that by 746 to get us the total power. One thing you don't want to do is what I did this morning, where I just wrote the power equaled 746, because I was like, oh, a number with watts after it. That's the power. You just got to be careful. That's just 1 horsepower is that, but I have 40 of them. So I need to have 40 times that. 29,840 watts. My final velocity is going to be 15, because that's the velocity I'm going to reach. My initial velocity is going to be 0. And the question is, how long will it take? You tell me. If I ask you how long something takes, what are you solving for? Time. Don't need to take a physics class to answer that question. If I ask you how long something takes, it's time. Okay. So just to write out this equation, what energy? I've now taught you two equations that we can start with. We can have kinetic energy initial, and we can have potential energy initial plus work equals kinetic energy final plus potential energy final. As we learn more energies, we just chuck them in. And we just ask ourselves, do I have these things? So, you tell, and then you're like, but this isn't what we're solving for. There's one more equation we're going to chuck in here. If ever you see power involved in a problem, remember there's literally only one equation with power in it. It's not even like you have to choose from the equations. There's literally only one with power in it. What is that equation? It's one I talked about it was a while ago, 40 minutes ago or something. Power equals, you tell me. Work over time. Power is how much energy you use every second. So if I can find the work, then I can find the time, because I know the power. And yay. All right, so we go to our energy equation. Currently, we don't know the work. Clearly, if I want to find time, I need work and power. I only have power. So we just go to the energy equation and we say, am I moving in the beginning? You tell me, am I moving in the beginning? No. My initial velocity is 0. Boom, that term goes away. We need to draw a picture of this because we need to make a decision. Where would you all like this car to... Well, okay, I'm going to decide. The car's on the ground. Where would you all like to make 0 in this problem? Where would you all like to make 0 height at or 0 Y position? What makes our life nice and easy? The ground. Great. We're going to start at the ground. We're going to say the ground is 0. Later on, in part A, does my car go up or down at all? So in part B it will. Part A, though, doesn't say anything about going up or down, so it just says how long will it take a car to go this fast. So we're going to assume flat ground. So, it starts on the ground, it ends on the ground. So, long story short, am I above 0 or below 0 in the beginning? No, there's my car. I'm at 0. So what's my potential energy to begin with? Also 0. So this term's also 0. And then we go to the end. Am I moving at the end? Yeah. I have kinetic energy at the end. Am I above or below 0 at the end? Nope. I'm at the ground still. I'm at 0. That's always the important thing. I keep saying ground, but 0. I'm at 0. So we just write this. If I cross it out, that just means it's 0. So 0 plus the work done equals the kinetic energy, 1/2 mv squared, plus 0. So I'm kind of going through and I'm writing all these things. My hope as time goes on is you do this kind of mental check in your head. Do I have kinetic? Do I have potential? Do I have a spring when we get to springs? Or if you really want, just write it out like I am. Write out the big old checklist. So work is just going to be equal to 1/2 mv squared. mv final squared, which is just going to be 1/2 times 850 times 15 squared. That's going to equal 95,625 joules. I'm going to shrink everything because I just need a tiny bit more space. You always need to keep sight of what you're actually solving for. So in this problem, it didn't ask for work. That's just an intermediary step. Never just stop at the first calculation and say, I'm done. Always actually remember, what the hell am I solving for? If you forget that, then you won't get the answer. So now we're going to do the thing we're actually solving for. Power equals work over time. So 29,840 equals my work, which is 95,625 over time. If you rearrange this, you're going to get that time equals 95,625 divided by 29,840. And yeah, that'll come out to 3.2 seconds. So that's part A. Part B, you go through the exact same process. The only thing that changes is now my car is going to go up a hill at the end. So what's going to change there? My potential energy at the end will no longer be 0. And you just solve the problem the same way. So I'm going to write that out, but that's one of those, do not look at my worked out solution to figure out how to solve this. I can't say this enough. Never, if you study purely by looking at worked out solutions, it is absolutely useless. It's like learning how to drive by watching a bunch of videos of people driving and then saying, I can do it, and assuming that's going to go well. I do not want someone on the road who has learned how to drive, who has never gotten in a vehicle and only learned by watching videos of it. It's not going to go well. So just to kind of write this out again, kinetic energy initial plus potential energy initial. Oh, and here they're moving. Here's 0. Here is y equals 3. So kinetic energy plus potential plus work equals kinetic energy final plus potential energy final. So yeah, the beginning, these are all still 0, but the new thing is that my work will be 1/2 mv final squared plus mg y final. we're no longer at we're no longer at 0 at the end. You do the same process, and it's great. So yeah, there you go. We didn't get to springs, but that's pretty straightforward. Next class, if you want to preview, try to solve this one on your own. It's a really good one. I like it a lot. We're going to start next class. It'll be one of the first ones you do. But yeah, there you go. We'll see y'all Tuesday. I'm going to guess the next class is a test. Yeah, I can tell. So I was like, when people show up early, it's because there's a test.